Hi guys, welcome back to Calculus with Mr. Robeson. So in the last video, we introduced the concept of related rates. All right, so how to solve equations that have something that's changing, something with a rate of change, and all variables are changing with respect to time. So then this one, we're just going to look over the rules one more time, or the steps one more time, and then just practice, more practice examples. All right, so again, we want to list what's given. We want to draw a picture. We want to make an equation or take the equation they give us and then take its derivative. Then we want to plug in. Sometimes you may need to do a little bit of extra work to get some other missing variables, say, and then we solve for what's required, and don't forget to put the units there. All right, so this is the classic two boats problem. So one boat leaves the dock traveling due north at 20 miles per hour. Another boat leaves from the same dock an hour later traveling due east at 30 miles per hour. Exactly 2 hours after the first boat leaves the dock, so that's 1 hour after the second one does, how fast is the distance between the boats changing? All right, so what do we have given? So we have one boat going due north at 20 miles per hour. We've got another boat headed due east at 30 miles per hour, and we want to know how fast the distance is changing. All right, so let's draw a picture here, and then we can label some variables. So let's say, here's our dock. Looks like a dock, right? We got one boat going due north. We got one boat going due east. All right, we can label these with whatever variables we want. Usually when I'm working with triangles, because we want to know the distance between them, here's the distance between them. And this will be a right angle, since due north, due east. Usually when we're working with triangles, I'll use A, B, and C. But you can also use X, Y, and Z, or whatever you want. But I'm going to call this side A, I'm going to call this side B, I'm going to call this side C. So B is going north. This is going east. So that means this 20 is dB dt. 20 miles per hour. If you want to write it like this instead of mph, that's fine. 8 is 30 miles per hour, so dA dt. All right, and we want to know dC dt after exactly 2 hours from when the first boat left. All right, so we've got our givens, we've got a graph, we need an equation. So we need some sort of equation that relates sides A, B, and C together. All right, so it's a right triangle. The easiest equation to come up with that relates those three sides is A squared plus B squared equals C squared. Good old Pythagorean theorem. That's the equation we're going to use. We take the derivative. So we bring down the 2. We get 2A dA dt plus 2B dB dt equals 2C dC dt. We'll get this same equation a lot. If you want to, you can cancel out all the 2's. Everything's divisible by 2, so you can just divide everybody by 2. Gone. All right, so there's our derivative. Now we're going to plug in. So we've got dA dt. We've got dB dt. We're trying to find dC dt. But we don't necessarily have A, B, or C. So we have one thing that we're trying to find. That means we have to have all the other variables. So we need to do some extra work on this one. So this one involves some extra work. So let's see, we go back to the problem and we say, let's see, one's going due north at 20 miles an hour for 2 hours. All right, well, 2 hours times 20 miles an hour, that means this B here, that's our length going due north, is 2 times 20. 40 miles. All right, our A here, so A left an hour later, leaves from the same dock an hour later. So that means it's only going for 1 hour, and it goes at 30 miles an hour. So we get 30 miles for the other side. So now we've got A, we've got B. Can we find C? Well, sure we can. We just have to plug back into the original. So we get 30 squared plus 40 squared equals C squared. All right, well, you can work this out if you want, but this is a 3, 4, 5 right triangle. It's just each side is times 10. So this will be 5 times 10, or 50 miles. So they are 50 miles apart at this exact moment. Right, so now we've got C. So when I say that there's extra work, that was the extra work step. So now we can plug in. So we've got 30 for A times dA dt, which is also 30, plus B is 40 times dB dt, which is 20, equals C, which is 50 times dC dt, the distance between them, the rate the distance between them is changing, and that's what we're trying to find. So we get 900 plus 800 divided by 50 equals dC dt. And if we throw that into our calculator, that's 1700 over 50 gives us that this here is 34. All right, now this is the rate that the distance between them is changing. All right, this distance is measured in miles, just like with everybody else, and its time is measured in hours, so this is going to be miles per hour. Now, before we stop and say that we are done, we need to check and make sure that this makes sense. Just a little look around. So 34 miles an hour. This is going at 30 miles an hour. This was going at, 20 miles an hour going up, 30 miles an hour going to the right or east. It makes sense that the distance would be increasing a little bit more because this distance is going to be a little bit longer. Right? So the hypotenuse distance should be a little bit longer than the other two, or the hypotenuse rate of change should also be longer. All right, let's take another look at a triangle problem. So an airplane is flying on a flight path that will take it directly over a radar tracking station as shown in the figure. So here's our airplane. It's flying forward, not backwards. If S is decreasing, so S is right here, the hypotenuse, missed it, there we go, is decreasing at our rate of 400 miles per hour. When S is 10 miles, what is the speed of the plane? So how fast is this going forward? Well, this going forward should be the same rate as this distance is changing. All right, so we've got S is 10 miles. We've got ds dt, the distance between the radar station and the plane, this diagonal distance, is negative 400 miles per hour. And we want to know dx dt. That's the horizontal distance from the plane to the station. How fast is the plane going is how fast that will be changing. This will be decreasing, the plane will be increasing. So we'll just remember to switch the sign at the end. All right, so we've got our givens, we've got our graph, we need an equation. The equation that relates these sides, right? So they were told, I guess, that the plane is flying 6 miles high. This side is not changing. All right, so the equation that relates these sides will be x squared plus 6 squared equals s squared, right? A squared plus b squared equals c squared. That's really all that we're doing. Right, you can do either one if you want, and then the rate of change of this side b would just be 0. All right, so this 6 squared is just 36. So now we can take this derivative. So we got our equation. We take its derivative. We get 2x times dx dt. Derivative of 36 is 0. And this gives us 2s times ds dt. Now, if we didn't realize that this side was 6 and we just used another variable, when we took its derivative, it would be 0. dB dt, if we labeled that side b, if we said this was b, dB dt would be 0 because the plane is not going up or down, it's flying level. All right, so that term would eventually cancel out either way, even if we made that mistake. It's not really a mistake, it's just doing it a different way. All right, here we can divide both sides by 2 to make our lives a little easier. So now we're going to go ahead and try to plug in. So let's see, do we have x? No, we don't have x right now. So we don't know x yet. dx dt, that's what we're trying to find. All right, so we definitely don't have that. S, we've got s is 10. ds dt, yeah, we've got that. That's negative 400. All right, so we need x. So now we have our extra work step. We need to solve for x. So we go back to this guy, and we can use the s that we have is 10, and we can plug in and solve. So we'll get x squared plus 6 squared equals 10 squared. All right, it's another 3, 4, 5 right triangle where all the sides have just been doubled. So it's a 2 times 3, 2 times 5. This is going to be 2 times 4. If you don't see that, that's fine. You can work it out. Subtract the 36. Take the square root. X does equal 8 either way. And this is also in miles because S was in miles and this side over here was in miles. So now we've got x, we can plug in, we've got 8 times dx dt equals 10 times negative 400. Divide both sides by 8. So we get 10 times negative 400 all over 8. So let's see, that's going to be negative 50 times 10 is going to be negative 500. So it's going 500 in the negative x direction. So that means our plane, how fast is the plane going? So the plane speed equals 500, and it is in miles per hour. You can also write mph if you want. The plane is going forward at 500 miles an hour. This side is decreasing at 500 miles per hour. Seems like our normal speed for a plane, 500 miles an hour. So, make sure that your answer makes sense. Next up, so it looks like we've got a shuttle taking off here. All right. If you ever get a chance to go to a shuttle launch, they're really cool. The ground shakes. It's like a big earthquake. All right. A television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position S equals 50t squared. So that is what S is. It's 50t squared. So now we have an actual equation for S, a formula for S. S is measured in feet. T is measured in seconds. So we have units and time here. The camera is 2,000 feet from the launch pad. So here's our camera over here, 2,000 feet away. This distance is not changing. Find the rate of change in the angle of elevation of the camera shown in figure 10 at 10 seconds after liftoff. So we want to know what this rate of change in the angle, d theta dt, is. All right, so we've got a graph already. Here's our graph. We've got some givens. We've got that S is 50t squared. We've got that t is 10 seconds. We've got that we're 2,000 feet away, which is already labeled. If we want, we can plug in this t right now and figure out exactly what S is. We're probably going to have to do it later if we don't do it now. But S at this exact moment is 50 times 10 squared, which is 50 times 100, which is 5,000, and that's in feet. So that means we're almost a mile up, and this picture is not exactly to scale, but that's okay. All right, now we need some sort of equation that relates this angle, this side S, and maybe this 2,000 that we already know. All right, well, something that relates an angle to two sides is going to be a trig function. This is the opposite side. This is the adjacent side. The trig function that works with opposite and adjacent is tangent. So we probably want to say that tangent of theta equals S over 2,000. Now we can take the derivative here. All right, so we've got our givens, we've got our graph, we've got our equation. So now we're going to take our derivative. Derivative tangent of theta is secant squared theta times derivative of theta, which is d theta dt, equals, well, this is 1 over 2,000 times S. Derivative of S is ds dt. Now, we can actually find ds dt. So we're trying to plug in here. We don't know theta yet. We're trying to find d theta dt, and we don't know ds dt yet. All right, but ds dt we can find. So we can take this formula, and we can take its derivative with respect to time. So we bring down the 2, so we get 2 times 50 is 100. Oops. T to the first times dt dt. Well, we don't need that. And we know that t is 10, so we can find that ds dt is 100 times 10, or 1,000. Right. And it's the rate of change in S, so it would be in feet per, what are we working in, seconds? There we go. 1,000 feet per second. Yeah, that seems pretty fast. The shuttle's moving pretty quickly. So now we've got ds dt. We need secant squared of theta. So we don't actually need theta. We need secant squared of theta. So at this exact moment, we already calculated that this height is 5,000. This is 2,000. We could get this side, and then we could get secant, because secant of theta is, well, it's hypotenuse over adjacent. It's cosine flipped over. All right, we've got the adjacent side. We need the hypotenuse. So to get the hypotenuse, I'm just going to call it x for now, we'll get that 2,000 squared plus 5,000 squared equals x squared. All right, so we can solve this. I'm just going to type it in my calculator. And after doing that and simplifying, we would just get that x equals 1,000 times the square root of 29. If you want to, you can write that as a decimal. It's 5,385.1648 or 165. All right, I'm going to leave it as the 1,000, whatever. So that means that the secant of theta will be this 1,000 times the square root of 29 over the adjacent, which is 2,000. All right, the thousands are going to cancel out. We're going to just get square root of 29 over 2. Remember, we want secant squared, though, so we can square that, and that's just going to be 29 over 4 times d theta dt equals 1 over 2,000 times ds dt, which is 1,000. So this is 1/2. The thousands are going to cancel out over here. Multiply up the 2, so that's going to cancel there. Actually, we want to multiply this over. So we're going to get that d theta dt equals 1/2 times 4 over 29, or 2 over 29. All right, our units here is this is the rate of change of an angle. All of our angles are in radians, so it's radians, and it was per second, s seconds. So there's our answer, 2/29 radians per second at this exact moment. All right, next up, the distance between a point and a curve. So find the rate of change of the distance between the origin, remember that's the point 0, 0, and a moving point on the graph of y equals sine of x if the rate of change of x is 2 centimeters per second and x is pi over 2. So what's happening here is we've got a point that is moving from the origin and it's following the sine curve. And right now it's at pi over 2. So right now the point is right here and it's moving along this curve at 2 centimeters per second. So this is our dx dt. Actually, I guess it's just moving over at 2 centimeters per second, dx dt. Just straight that way. It's also going to be moving down, but it's moving along the curve here. And we're starting at the point 0, 0, and we've got that y equals sine of x. So this function here is y equals sine of x. And we're going from the origin to this point. All right, so what we need to do is come up with a formula for the distance between this point and the point on the curve. All right, well, we can either just use the distance formula or we can make it a right triangle, which is the exact same thing as using the distance formula. So there's our right triangle. This is our x, this is our y, and this is going to be, maybe I'll call it d for distance. We can also go a and b and c if we want. So we can set up our equation, x squared plus y squared equals the distance between them squared. We take the derivative of this, we get 2x times dx dt plus 2y times dy dt equals 2d times dd dt, the rate of change in distance with respect to time. The 2's are all going to cancel out. It's nice how they always do that. We've got x is pi over 2. We've got dx dt, it's 2 centimeters per second. We've got, well, we could get y. All right, we can get y because we've got the point there. So y is going to be sine of pi over 2, which is 1. So now we've got y. Can we get dy dt? Well, sure, we take the derivative. dy dt equals, derivative of sine is cosine. Cosine of t, or sorry, cosine of x is our variable, times derivative of the inside, which is dx dt. Right. Cosine of x at pi over 2, so we got cosine of pi over 2 times dx dt, which is 2. Cosine of pi over 2, though, is 0. Remember, cosine starts high and comes down? So this is 0 times 2, which is just 0. So this is 0. Do we have the distance between them? Well, no, but we can use the Pythagorean theorem to find it. It's just going to be pi over 2 squared plus 1 squared equals the distance squared. So if we just take the square root of both sides, that's going to give us our distance. So now we can plug in because we've got d. So we got x is pi over 2. dx dt is 2. Y was 1, dy dt is 0. That's going to go away. Our distance between them is going to be the square root of pi squared over 4 plus 1, just squaring that guy out, times dd dt. Now we can just divide this over. So these 2's are going to cancel out. That's 0. So we get pi divided by the square root pi squared over 4 plus 1 is the rate of change of our distance. All right, I didn't write a units in here. Our units should be the same, centimeters per second, so it's centimeters per second. And there we go. Oh, it just keeps going. Thought we were done. The formula for the volume of a cone, we've worked with that once before. Find the rate of change of the volume, so that's dV dt is what we want. I'm just going to write it here, dV dt. If dr dt, the rate of change in the radius, is 2 inches per minute, and h is equal to 3 times the radius. So the height is always 3 times the radius. So we've got some options here if we've got this. Either we can take the derivative of this to begin with, or we can just get rid of h right from the start and plug 3r in for h. In which case, we get volume equals 1/3 pi r squared times 3r. And this 3 and 1/3 is going to cancel. We get r to the third. So our volume is pi r to the third. All right, we've gotten rid of h because we don't need it. All right, and it has another formula. It's just 3r. So that means dV dt, bring down the 3, we get r squared times dr dt. All right, so there is our derivative formula. All right, at r is 6 and dr dt is 2, so we get that dV dt equals 3 pi times 6 squared times 2. And we're just working that out. It's going to be in volume. We're working with inches, so it's inches cubed per minute. All right, with the other one, r is 24, so we get dV dt equals 3 pi times 24 squared times dr dt, which is 2. And again, this is inches cubed per minute. I'm not going to work those out in the interest of time, but you can if you want. Oops. All right, so that's it. So that was more related rate practice. Sorry if this one's a little long. All right, we'll get working on the homework. I expect to work out, honestly, almost all the homework questions in class. So try each one, see what you can get through, and then we'll work it out together in class, okay?